Okay, hi Jan. The floor is yours. Please give us your presentation about the PRAT2 proposal.
Thank you. Good morning and good afternoon. On behalf of the PRAT collaboration and also
muted, I think.
Can you hear me?
Yes, you were fine.
But somehow someone was saying something.
I think Marcus forgot to turn off his mic. You can go back into presenter mode.
Okay. Good morning and good afternoon. On behalf of the PRAT collaboration and also all the spokespersons listed here, I'm presenting on the proposal on PRAT2, which is a new upgraded high precision measurement of the proton charge radius. Here's the outline of this presentation. I will briefly review the physics motivation, then I will show you the PRAT experiment and the results, and followed by PRAT2 overview. Then I will go through the proposed measurements and improvements. And towards the end, we'll make the beam request and also show you the projected results and followed by a brief summary. For the proton charge radius, this is a quantity most of us here are quite familiar in terms of its importance, not just from the QCD sake, as it is an important quantity related to the proton structure, but also highly important for atomic physics in terms of QED calculations. For example, the proton charge radius can affect the muonic hydrogen length shift energy level difference by as much as 2%, and it also is critically important in determining the Rydberg constant. So many of us also are very familiar with the proton charge radius, which was triggered by the large discrepancy we have seen in 2010 from the muonic hydrogen measurement, and the proton radius was found to be several close to 6 sigma smaller than the cold data compilation at the time, which came from hydrogen spectroscopy and also electron scattering compilation. So there are three methods in general, or two large categories of measurement approach. One is spectroscopy, in which one can use both ordinary hydrogen spectroscopy as well as muonic hydrogen. And there's also the lepton scattering, elastic scattering from nuclear particle physics. For example, PRAT, which is an EP elastic, and mine is EP elastic. But one can also do mu-P elastic scattering, like MUSE at PSI and also COMPASS++ AMBER, which is planned at CERN. One thing is important is that these two large categories of measurement, in the end, we are measuring the same quantity, which is defined here by the slope or derivative of the proton electric form factor at Q square equals 0. And this point was made very clearly by Jerry Miller last year. So let me just very quickly review PRAT experiment. It was proposed to help solve the proton charge radius puzzle by using a high resolution large acceptance hybrid calorimeter. So this advantage is one can access very forward angle at the same time. You can take many Q square data points at the same time. And we also used a large area gem detector for better precision resolution, which is directly related to the Q square determination. And to suppress the background, especially from the target window, we used a windowless hydrogen gas target, which is for the first time at Jefferson Lab. And for cross-section measurement, it is extremely important to have a luminosity reference. Yes?
We lost your audio for a second.
Can you hear me now?
Yes.
We reached lowest Q square 2 times 10 to minus 4 GeV over C, which was the lowest ever achieved. And one also very important component is the vacuum chamber to suppress the beamline suppress the background. So here show you the results from PRAT, which was published, as Stuart also mentioned, last year in Nature. So we measure a proton radius, which is 0.831. And this number is consistent with the muonic hydrogen measurement, as well as two recent hydrogen atomic spectroscopy measurement. And the PRAT result recently was included in the latest particle data group. And the code data in 2019 revisited the compilation of the proton charge radius, and we believe the PRAT preliminary result also played a role in that. And to reanalyze or reassess the code data value in 2019, the Rydberg constant also has been shifted by 5 sigma also. So this is actually a very important and a high impact result. So why PRAT2? What is very important is PRAT, as for the first time, demonstrated the power of magnetic spectrometer-free calorimetric method for proton charge radius measurement, but it has not reached its ultimate precision for this kind of new technique. And PRAT is also the first electron scattering experiment measured a proton radius that is consistent with muonic results. And we determined the electric form factor quantity from our experiment, and our data show systematic difference from those from mines, which the most precise measurement. So therefore, high precision is demanded in order to understand this difference. There is also a very interesting question many people have asked and looked into, which is whether there is a potential systematic difference or difference between proton radius determining electronic system versus muonic. And that question can only be answered when we have ultra high precision. And another very important aspect is pushing this technique to the highest precision will also opens a new window of opportunities for future precision electromagnetic physics at Jefferson Lab. So how do we do this? And what is the goal of PRAT2 and how? So we will reduce the overall uncertainty on the proton charge radius measurement by a factor of 3.8. And I want to mention this number is different from what's in the proposal, and that is based on the full simulation, including all the upgrades we propose to do. And we will reach the unprecedented low value of Q square, which is 4 times 10 to minus 5 GeV over C square. And this also was strongly endorsed by the series TAC report. And how do we do this? So we will improve the tracking capability by adding a second plane of tracking detector. We will also add new rectangular cross-shaped scintillator detectors to separate molar electron from EP electron in the scattering angle 0.5 to 0.8 degree. And we also want to upgrade high-cal by replacing the lead glass blocks by the crystals. So that will improve the uniformity of both the energy and position resolution, and also suppress the inelastic background. And we also want to convert the readout to flash ABC readout. And we also want to suppress the beamline background by improving the beamline vacuum and also adding a second beam halo block upstream of the tagger. And we will reduce the statistical uncertainty or error bar by a factor of 4 compared with PRAT. And we propose to use 3 beam energies, 0.7, 1.4, and 2.1 GeV. And 0.7 GeV, I want to emphasize here, is critical in order to reach the lowest Q square proposed. And we also have planned to do improved rate of correction calculation by going to the next leading order. And we talk about potential target improvement, but that was not used in our projection. So let me just briefly show you the overview of the apparatus. And in the interest of time, and I will emphasize on the difference from PRAT. So we will add a second beam halo block here upstream of the target, and we will have 2 tracking detectors, and which are shown here and separated by a helium bag. And we also have a scintillator which will be mounted inside the target chamber upstream of the target. So very quickly remind you what we are going to measure. So we're going to measure cross-section differential cross-section from EP. And so I show one photon exchange, but for our kinematics, the two photon exchange effect, which we have looked into for PRAD2, is negligible. Given the kinematic range of our experiment, our cross-section is dominated by the electric form factor. Nevertheless, we have taken into consideration the magnetic form factor contribution to the cross-section, and also assigned systematics associated with what kind of GM we use in our data analysis. So here shows the what we are trying to do, and I mentioned earlier we use molar as a reference. So here shows the differential cross-section experimentally how we're going to relate to the molar scattering. So there are two ways one can relate that. One is beam by beam method, and that method allow you to cancel out energy independent part of efficiency acceptance, but you have a limited coverage due to the acceptance for double arm molar measurement. The other method is so-called integrated molar method, which allow you to use the fixed angular range, apply that to all the EP Q-square beams, and one need to know the GM efficiency very well for that method. And both cases that the luminosity canceled. So in the PRAD case, we have to combine beam by beam method and also integrated molar method together because of the acceptance issue, and also because we only have one GM detector, so the efficiency of GM is not known extremely well. And in PRAD2, with two tracking detector, we will be able to use integrated molar method. And I also mentioned that we have planned to improve the rate of correction calculation, but even in PRAD1, we have two independent event generator to take that into consideration. And in the end, we actually do an iterative procedure to compare data with simulation. So let me very quickly to show you the kind of improvement when we have two tracking detectors. So here shows the lower figure shows the GM efficiency in XY plane for what was used in PRAD. And because we have to have a spacer in between the GM layers so that the efficiency has drops when you have a spacer, but one can remove that offline, which will show much more uniform GM efficiency. But with the new technology, micro-resistive well detector, one can actually go with spacerless this type of tracking detector, and also the position resolution also improved somewhat compared with the GM, which is more around 70 micron. So for PRAD2, let's just take a look at when we use two GM as tracking versus two new micro R well tracking detector. So here shows the efficiency plot, which is hardly one can see the difference. But the lower figure shows the distribution of the uncertainty of the distribution. And you can see that the new technology is somewhat better, but what PRAD has accomplished already based on that well-established technology also will do quite well. So here, let me show you the kind of improvement when we use two tracking detectors in terms of the efficiency versus uncertainty, PRAD2 compared with PRAD, and also the angular resolution determination when we have two tracking detector with the high cal upgrade, as well as the Q-square resolution. Another very important aspect is the background subtraction. And in PRAD, why we overall have background under good control by taking measurement with different combination of background are wrong, but the fact that just having one tracking detector limited our Z-target resolution. So with two tracking detector, you can see the improvement when we compare PRAD2 in black and the PRAD. So this one is a little bit, let me walk you through here to show two planes of track detector and with the potential rate of correction calculation, how we can improve, how much we will improve compared with PRAD measurement. So if we use two GM detector just like PRAD, and if we just use PRAD method, which is one tracking detector, and we have to combine beam by beam and integrate molar method. So you will see on the left, you will see these black points. Okay, so you adopt PRAT method exactly for PRAT2. That's what you will get. So now when you use two tracking detector, you will get the red points here. Okay, so that already improved the systematic enormously. So then when you also add potential radial correction improvement, you get the blue point. So the most important point is the uniformity or angular dependence or Q-square dependence. We will be able to determine the cross-section. And so on the right-hand side shows that kind of improvement in the determined radius. So if we just use the PRAT method, and that's what we will get, the uncertainty is 0.0069 from PRAT. And if we use the PRAT2, but the PRAT radial correction, and the improvement is already very significant. So we get reduced to 0.0015. And if we use the anticipated new radial correction, and the improvement will be significantly reduced to 0.0004. And with high cal improvement, we want to replace all the lead crystal to the crystal, lead glass by crystals. And so this will significantly improving the uniformity and also better position and energy resolution. And this improvement will also help us in a major way in suppressing the inelastic contamination. So here shows the kind of contribution due to inelastic when you are in the lead tungstate crystal region. And here shows the lead glass region. So if the high cal is completely replaced by all crystals, then the inelastic contamination will be negligible. And this is actually very important. Another important aspect is to...
You have 5 minutes left.
Another important aspect is to change to flash ADC, which will allow us to take data at a rate which is factor 7 compared with PRAT. Okay, so we want to access to the smallest possible Q-square. One is to go to low beam energy 0.7. Another very important aspect is being able to differentiate EP event from molar event at small angles. And the high energy molar events will mimic EP elastic events at the forward angle. However, the low energy molar, which is the second arm, that falls out of the acceptance of high cal. So in order to still catch those low energy molar events, so we add this kind of cross scintillator for a scintillator detector. So that will allow us to suppress those molar events. So we can detect EP elastic events at forward angle 0.5 to 0.8 degree. So here just show you the kind of study we have done in order to demonstrate that we can extract the proton charge radius in a very robust way. So here show you the kind of input, which is PRAT data, fit to second order polynomial, then use that to generate as pseudo data for PRAT2 and look at what we are able to get out for the proton charge radius. So what is the beam requirement and the request? So we talk about 0.7, 1.4, and 2.1. And for the beam current, for the low beam energy, 20 nanoamp, and then the other 70. And we also list the kind of position stability and the beam size. And we don't need polarization, but polarization will not hurt the experiment. And we want the beam halo to be on the order of 10 to minus 7. And here shows the beam time request, including detector calibration, checkout test, and production data run, as well as empty target run. So empty target run is lumped together here. And we also budget 1 day for beam energy change. So the total measurement, for the total experiment, we require 40 days. So we also have addressed all the TAC questions, and these are outstanding questions, and we provided answer to the PAC readers and also the chair, as well as the user group chair. So let me just take a minute to show you the final improvement we will be able to get. So the top one is statistical uncertainty, PRAT2 compared with PRAT. And we also list all the systematic uncertainties, and then the final bottom line, which the improvement is factor 3.8 compared with PRAT. And on the right-hand side shows what kind of contribution which will lead to this kind of improvement. For example, more beam time will give you smaller uncertainty, and then tracking and high cal and so on and so forth. So let me just show you the projection here. So we show you the projection for both the differential cross-section for the 3 proposed beam energy, as well as systematic uncertainties are shown as arrow bands or bands here, shaded area here, and the color code is for different beam energy. And the upper left one is differential cross-section, and the upper right one is electric form factor. And it is very important to have these overlap, even though I mentioned that with high cal, we are able to take many Q-square beam at once, but we do need to vary the beam energies. Therefore, it is important to provide the kind of sufficient overlap between from one beam energy to another. And 0.7 degree or 0.7 GeV, again, is important to reach the lowest Q-square. So the bottom figure shows the projected PRAT2 measurement on RP together with PRAT, as well as all the latest measurements since 2010, the precise one. There are also a couple other not included here, as well as co-data compilation 2014, and the most recent one is somehow 2018 is not here. I apologize, but it's in the early slide. Okay, so let me just summarize. PRAT experiment demonstrated the power of calorimetric method for the proton charge radius measurement, and we reported high impact result on the proton radius. And PRAT2 will push for the precision of such method and improve the RP measurement by a factor 3.8. And high precision data from PRAT2 on GEP will help resolve the differences between PRAT and other modern EP experiment, and particularly perhaps the A1 experiment at Mainz. And high precision result on the radius from PRAT will also allow us for systematic study or investigation in terms of result from EP and muonic hydrogen measurement. And I hope that we have shown you that PRAT2 with the kind of proposed ultimate precision may open a new window of opportunities for precision electromagnetic physics at Jefferson Lab. Thank you.
Thank you very much, Payam. The questions will be started by the first reader of the proposal, who is Concentina Scienti. Please, Concentina. Concentina, can you hear us?
I see her mic is on, but I do not hear her voice.
He said it in the chat, Lorelei, that we can't hear her. So move to Stefan, she says.
Okay, maybe then while Constantina tries to get her mic going. Now, the sensitivity to the radius largely comes from the high Q-square. Did you make a check how much you would lose in sensitivity if you would leave off the 1.4 GeV run? So you have the lowest one, which is, well, it's always nice to sort of get to the lowest Q-square you ever have out of curiosity. And you combine this with the high momentum run and you leave off the 1.4. How much would this change in accuracy? Would you see any effect?
So I do not. We have done so many studies, as you probably have seen from the response, and this particular one, I will ask one of my colleagues to address specifically, but okay, so maybe I will ask Jingyi Zhou to see whether she has looked at this, and then I will answer. Depends on whether she has looked at this or not.
Okay, thank you. Now, if Konstantina, are you on?
So let me just answer this question then. Things looks like somehow Jingyi Zhou is not able to answer. Based on what we have done and also based on what we have looked at in PRAT2 case, and I think that the impact in terms of the precision is not going to be major. Having said that, however, it is very, very important to provide the full overlap. And 1.4 overlap with 2.1 is particularly important in terms of higher Q-square region. If you recall, actually our data, GEP, have a systematic shift or difference with between our data and the mines. And this actually difference is more pronounced at higher Q-square. So that's why 1.4 is very important to provide the important overlap with the 2.1 at higher Q-square range.
I can see the importance of having a cross-check. I mean, you can look for systematics if you correct for your Muller, and if your radiative corrections are done well, then you should not see a difference in the extract basically between the 1.4 and the 2.1 GeV. However, of course, you can never use data twice. So you can use the 1.4 GeV to cross-check your radiative correction, and then use the 0.7 and the 2.1 to do your actual fit.
Well, I think that one thing we need to keep in mind is that because we are taking data at different time, 0.7 and 1.4 and 2.1, so you do want to make sure there is no systematic from one beam manager to another. And 0.7 is actually quite low, as you can imagine. So I think that having 1.4, will be very helpful. But I see your point also.
And then maybe another one, you promised new radiative correction calculations, which are extremely challenging. We recently listened to a radiative correction workshop in Stony Brook, but we could get very little information on the status of this new approach to calculate the radiative corrections, which you mentioned in your proposal.
Yeah, I think you're right. So there are two theorists. Both one is actually very well recognized theoretician who is an expert in radiative correction, and they're both at Duke. And so they also have a collaborator. So right now we're working on a proposal to DOE to actually request support for this calculation. And you're absolutely right. It's very difficult. But we also have heard at Stony Brook workshop that Herbert Spearsberg at Mines has already, or they are publishing their work very soon, which is the two-loop RC calculation for the P2 experiment, which we reached out to him. And I also showed early that even without what we really wanted, right, to have, but the final impact on our radius for PRAT2 is not going to be in a major way, as we showed here.
Okay, Concertina, do you want to try if you can speak now?
Can you hear me?
Yes.
Yes, we do.
Yeah, hallelujah. Hi. So I don't know what Stefan asked while I was trying to convince this program to hear me. I've asked this question already. You have tried to answer, but I'm still not convinced. If I look at the proposal, or then the main difference, or if you want the reason why you get a different radius compared to A1, for example, is that your form factor is flattening. And I don't see why. So probably in the proposal, that was what we were trying to understand also with Stefan together, is that in the proposal, when you plot, yes, exactly, these plot, or the other one you have in the proposal where it's easier to be seen that there is a fundamental difference at larger Q square. There are no systematic errors included in the form factor. But on the other side, if they are not there, then I don't understand why they have no influence on the radius. So the radius you get is smaller because the form factor is flattened at higher Q square. That's just the reason why you get the smaller radius. Why should a higher precision solve the issue which you have? So this difference which you have with not only A1, these are all the previous EP scattering data. You have a very nice plot is the other one in the proposal where you really see that there is a difference in the GE at larger Q squared compared with the previous data.
Yeah, I think that let me go to one of my backup slides if that might be useful. If I can find it. Yeah, I don't know whether this one is better or whether this one
It might be your page 21 also, where you have the linear scale comparison.
Okay, I can go to page 21.
Is there 3 something in the proposal?
Page 21. This is not page 21. No. is a proposed measurement, and right. So we can look at this one. So I think that Konstantina, you actually have 2 questions. Basically, you're asking 2 questions, and one is GEP, one is radius. So I would like to remind everybody that the motivation we have here is one is to improve the RP measurement, really push the precision of PRAD to the highest level we can achieve. And that's one of the important motivation. And of course, RP comes from GEP, electric form factor. So we also want to obviously to improve the electric form factor measurement of the proton, right? To improve our precision. And you know, so when you have improved precision and when you have better measurement, so for example, with only one tracking detector, we cannot, you know, reject background extremely well, for example, right, at forward angle, low energy, but also inelastic contribution when we have a high cal with a lead glass at the outside. So I'm just giving you, you know, a couple of examples. So there are things we wanted to really push our measurement. Every single step we want to do the best we can, right? The technology allows us. So that's why we want to do this experiment to improve what PRAD has done, right? And then to see whether, you know, our data has any systematic, right? We obviously cannot answer questions about other people's data, but we want to do the best we can. We want to address all the potential, you know, lingering aspect of the experiment, but we demonstrate this technique work and we want to do a much better job. I don't know whether I answer your question or not, but please let me know if I can invite.
Not really. You had it in your last slide. The conclusion is increasing precision would also help us understand the difference with the MINDS 2010 data. Now, my point, probably I'm a purist of error bars, but if I look at your plots in the proposal, that's the 3B, where you have GEP as a function of Q squared, and you have the error bars. And the error bars do not touch the MINDS data. So even if you reduce the error bars, you will be anyhow above the MINDS data. So again, I'm asking, how will an improvement, an improved precision on the PRAD2 data help resolve the difference between PRAD and all the other experiments?
Okay, I think I understand your question. So first of all, there are statistical aspects to data point. They're also systematic, right? So let's just assume in the widest dream, okay, for whatever reason, we are off by a factor, which actually perhaps it's more, you know, overall factor, okay, not point to point. Maybe it's an overall factor. So that will shift everything up and down, for example. I'm just saying the widest possible dream. That is, I'm not saying that's not impossible, but not likely, but right. So when you do a new experiment, you are not going to get GEP for the same Q square at exactly the same value, right? You maybe get very close, or maybe you're very lucky among all your data points, you have certain points which are almost exactly the same, but based on statistics, right? And then you also have systematics, overall systematics and point-to-point systematics. So that's why it's important to do the experiment when you know there are places you can improve, right? You're not going to measure the same thing 10 times. You're not going to measure exactly the same central value. You have the probability to exact central value, but in reality, you have systematic and statistics, but you want to make sure that overall, right, you don't see anything, we hope there are no major issue, and we think there should not be, but on the other hand, we are talking about a pretty small differences here.
Marcus, this is a short contact person. Can I add?
Yes, please. We'll have to keep answers short now because we're running quite late. Please.
Yes. Hayan already answered that, but I want to just simply conclude that what's the point here is that, yes, there is a visible difference between our GE and particularly mine's one, but extracted radius difference is only 3 sigma difference. That's not enough statistically to conclude anything in this field. And this was used in many workshops and many conferences that based on today's data, the difference between EP scattering results is not solved. And we want to make our sigma another factor of 3-4 times better in order to finally solve this difference. Either there is difference really serious or there is not. So that's a major question here. It's not GE that at larger Q square, there is a visual, for sure at smaller Q squares also there is a difference, but difference is naturally smaller. The most important thing is extracted radius and error on radius. Thank you very much.
Okay. Can I, Marcus, can I ask a very quick question? Another one, just quickly.
I suggest that in the meantime, we switch the screen sharing to the next speaker.
Okay, that is really quick because you sent me this very nice table of the error bars where I could just see what will happen when one thing or the other of the upgrade won't be in place. Did I understand it correctly that actually you could even reach a firm conclusion if you just leave the gem? So you just add an additional plane of gem and you just use gem in case all the R&D of the new chamber won't work.
Yeah, Constantina, absolutely. So actually, if you look at the final projection, so this one corresponding to 0.0036 Fermi in terms of overall uncertainty. If we use the PRAT gen technology, it will be 0.045 Fermi. So the improvement will be a factor of 3 instead of a factor of 3.8.
Okay, thank you. That was it.
Thanks.
Thank you very much for all. And I suggest we now switch to the next speaker, Dipankar Dutta, who will present the DRAT proposal. Please.
So I'm trying to share the screen, but I think Hayan is still sharing.
No.
Oh, okay. Now it's done. Okay. Okay.
I see your screen.
Is it full screen?
Yep. Beautiful.
And is the bar hidden? Do I need to hide the bar? Is it? I couldn't hear that. Is the bar hidden?
Yes.
Okay, great. So I'm going to present another proposal from the PRAD collaboration. This is a you can think of it as a companion experiment, but a different experiment, which will use the same technique to measure the deuteron charge radius using electron-deuteron scattering. Here's my outline. I'll start with a quick executive summary and then go over to the introduction and motivation for the problem, give you the details of the experiment, and conclude. So,
Dipankar, we don't hear you. We lost your audio.
okay, can you hear me now?
Yes.
Okay, so I'll go back. Hopefully it won't crash again. So here's my executive summary. So as I said, in previous talk, it was shown that the PRAD method convincingly demonstrates the advantages of the calorimetric technique. And so we want to basically use the same technique to measure the deuteron charge radius with a precision of about 0.22%. And this calorimetric technique will allow us to cover a large Q-square range, covering about 2 orders of magnitude, and also allow us to probe the lowest Q-square reached in electron-deuteron scattering experiments. The setup is going to be the same as PRAD2, but with a new recoil detector. And that's the major difference between the two experiments. So around the time when the proton radius puzzle came to be known, in a few years after that, the muonic deuterium spectroscopy measurements were performed to extract deuteron charge radius, and they came out to be about 6 sigma different from the co-data value for the deuteron charge radius. The co-data value is highly correlated with the proton charge radius. And so people then went back and looked at all of the deuteron spectroscopy results and extracted the charge radius just from the deuteron spectroscopy results or experiments. And there was still a large, significantly large discrepancy between the muonic results and the regular deuterium spectroscopy results. And therefore, we can conclude that in addition to the proton radius puzzle, there was also a deuteron radius puzzle. Unfortunately, electron-deuteron scattering has not been able to play any significant role in addressing this issue because most of the data is very old and have larger uncertainty. And in fact, the most recent result is a reanalysis of these 3 old experiments, which were reanalyzed to get this last point. And the error bars is large enough to basically span the entire range of the discrepancy. So it doesn't contribute to addressing this problem. And in addition to that, the electron-deuteron scattering was normalized to electron-proton scattering in all of these experiments. So this situation points to an urgent need for a high-precision electron-deuteron scattering experiment, which can cover a large enough Q-square range and also reach the lowest Q-square in electron-deuteron scattering for the first time. In the first Born approximation, elastic electron-deuteron scattering basically can be written as the cross-section for scattering from a point-like particle times 2 structure functions called the A and B structure functions, which are basically related to the deuteron charge, electric quadrupole, and magnetic dipole form factors, as shown here. At the low Q squares, the quadrupole form factor and the magnetic dipole form factors are small, and so one can write the deuteron RMS charge radius as the slope of the charge form factor at Q square of 0. Or in other words, you can also do it equivalently in terms of the slope of the A structure function at Q square of 0 plus some constant. And so this is the technique we want to use to extract the charge radius from the electron-deuteron scattering. And we want to use the PRAD method using the PRAD2 setup, but at 1.1 and 2.2 GeV electron beam energy. And as was mentioned earlier, PRAD2 setup will involve a new upgraded calorimeter with all lead tungstate crystals, which will be our version of the magnetic spectrometer free measurement. It will use the windowless target, which was used in PRAD, but with a new cell, as I'll explain. And it will involve simultaneous detection of elastic and molar, just like in PRAD and PRAD2, for control of systematics. The same large area vacuum chamber with a thin window and 2 coordinate detectors, either with GEM technology or with the mu-R-well technology, will allow us to get better resolution and allow us to get better resolution over the entire Q-square range, which will cover about 2 orders of magnitude in range and allow us to reach the lowest Q-square reached in electron-deuteron scattering. The new thing is this cylindrical recoil detector, which is needed to ensure elasticity of the reaction. And all of these together will then allow us to extract the deuteron radius in essentially model independent manner. The upgrade of the calorimeter to all crystal calorimeter was mentioned earlier in the previous talks. I won't go into too much details of this. I will move on to the parts which are different between DRAD and focus on these differences between DRAD and PRAD2. So one of the important differences is the target cell itself. Because we now have to accommodate this, the recoil detector, cylindrical recoil detector inside the target cell, so the target cell radius will be slightly different, it will be a little bit larger. And also because of that, the gas will be coming in from the side rather than from the top, as in case of PRAD2. But just like in case of PRAD2, the gas will be pumped out from these 2 millimeter holes in the Kapton windows here, providing a windowless target, just like in PRAD2. But the cell would have to be redesigned for this experiment. And that's why it is a different experiment. Just like in case of PRAD2, we will detect the elastic and the molar events simultaneously within the same experimental acceptance. This allows us to get rid of two major systematic error sources of systematic error, namely the number of electrons and the number of target nuclei, that is the luminosity, is cancels out. But we do need to know the relative detector efficiency and geometrical efficiencies of the two, between the two reactions. And for that, in case of DRAD experiment, in order to get the geometrical acceptance and detector efficiencies, we will need to do a calibration run with electron-proton scattering as our calibration channel using the hydrogen gas in the target cell. This will give us the proton detection efficiency. And to get to the deuteron efficiency, we will use the ratio of deuteron to proton detection efficiency, which we will measure separately at tunnel using this recoil detector and taking it to tunnel for measuring using the proton and deuteron beams that are available from the tandem accelerator at Tunnel and Duke University. So that's the method we will be using for the establishment of the detector efficiency. And the molar events will be detected in the 2-electron mode over some of the kinematic range and single electron mode, just like as in PRAD2 and PRAD. So that is not different. So now the most important difference is this recoil detector, cylindrical recoil detector, which will ensure that we are looking at electron-deuteron elastic scattering. This detector, we have chosen silicon strip-based technology for this recoil detector, which is based on the class 12 barrel silicon tracker, the SVT, which is a very successful and currently being used in class 12. But it's a redesign which is based on that particular detector, working detector. It'll consist of 20 panels or sensors of twin single-sided silicon strip detectors with a size of about 40 by 50 millimeter. This is significantly smaller than the SVT detector, which allows us to go to thinner the detectors can be thinner, like the first layer will be 200 microns and the outer layer can be 300 microns. But this can be further optimized because of the smaller size. It allows us to go to thinner detectors. The 20 panels will form a dodecagon with a radius of about 13 centimeters. And each sensor will have about 256 strips, which will allow us to get a azimuthal angular resolution, which is the most important direction, of 5 milliradians, and then also in the scattering angle about 20 milliradians. Another very important critical difference between the SVT and the detector we are proposing here is this passivation layer, or the dead layer on the silicon. We would like to have about 0.1 micron as our thickness, and this thickness is actually middle of the road these days. It is available from vendors such as Micron Semiconductors. And as I said, it's middle of the road of the detectors, not their best. They can go all the way up to 0.1 micron, or 0.01 micron. But we are choosing 0.1 for now because that provides enough. The threshold for Proton is about 20 keV, so that is more than enough for us. Also, as I mentioned, because we are going to a smaller detector compared to the SVT, that allows us a range of thicknesses, and so that thickness can be optimized to best suit our needs. Finally, there is also new technology of neutron transmutation doped type silicon, which allows a much more uniform passivation layer with less than 5% variation, and that would be very important for this detector because for DRAD we need as uniform efficiency as possible. So these are some of the improvements in the detector technology which is available over what is used in SVT. I mentioned we will be using 256 strips which have a linearly varying angle of 0 to 3 degrees, and that allows this angular resolution along the azimuthal of 5 milliradians, which is the most critical direction for us. And as I mentioned earlier, we will be calibrating the detector with EP elastic scattering on hydrogen to get the efficiency, and measuring the proton to deuteron efficiency ratio at tunnel. And we had began preparations to do a proof of principle test using one of the SVT modules and taking it to tunnel. We had identified a scattering chamber. We had started making all the arrangements, and we had even received beam time for April and May. However, that had to be postponed because of COVID. But we are still continuing with all the procurement of the feed-throughs and the cables that are needed in order to be able to do this proof of principle measurement at tunnel, hopefully in the short while. And now to talk about the particle identification that we do with this recoil detector, both at 1.1 and 2.2 GeV. The idea which we are relying on is the coplanarity of the electron-deuteron elastic scattering. And this ensures that there is this strong correlation between the azimuthal angle difference between the electron and the deuteron, and the time difference between the electron and the deuteron, which is basically the time difference between high cal and the recoil detector. And that basically works at all angles. It works especially well at smaller angles, and at the larger angles, there is a little bit of contamination. For example, in the worst case, we see from simulations that we expect to see about 0.2% contamination at the largest angle. And therefore, we would like to use certain additional constraints over this coplanarity in order to either clean it up or to monitor the detector efficiency during an experiment. And these additional constraints are things like the proton at the larger angles can reach the second layer, while none of the deuteron at this 1.1 GeV kinematics can reach the second layer of the silicon detector. And so, because the protons can reach the second layer, we have this additional constraint on the large angle protons, large scattering angle protons. Similarly, at 2.2 GeV, again, we are relying we are relying mostly on the coplanarity of the ED elastic scattering to separate protons from the background, the deuterons from the background protons, which come from quasi-elastic scattering. But in addition, we have some constraints at different angular ranges, especially at the highest angular, largest angular ranges. We have, because both the deuteron and proton can now reach the second layer, we can use the difference in energy deposition in the first layer versus the total energy to be able to have additional constraints which allow us either to do better PID or to monitor the efficiency of the detector. Finally, we had comprehensive Geant4 simulations based on the PRAD2 and PRAD setup, but adding this silicon detector into the mix, and we use that to show that we can achieve the high Q-square resolution over the entire Q-square range, and also more importantly to show that we can achieve detect these deuterons, the low energy deuterons at the lowest angles, if we have a passivation layer of about 0.1 microns, as I mentioned. At this passivation layer, at the lowest angle, which is 0.7 degrees for us, not only can the deuterons pass through this layer, but it has enough energy to produce a signal large enough compared to the noise. And so we should be able to detect the deuterons over the entire angular range of interest, which is 0.7 to 7.5. As I mentioned, we have added the comprehensive simulation includes all kinds of backgrounds, the major one being the electrodisintegration or the quasi-elastic scattering, which is about 6% of this elastic rate, so an inelastic, which is about 1%, and inelastic we can separate out just using the energy resolution of the calorimeter, which is shown over here. Finally, the simulation also includes radiative effects, and which were adapted from the PRAD experiment, the generators from the PRAD experiment, and for DRAD we include internal and external radiation, and it shows us clearly that we should be able to separate between the molar and the elastic over the entire angular range covered in the experiment. Finally, as for PRAD, we did a wide range of studies studying of the various functional forms to look for the robustness of the extraction of RD. And for that, we used the various modern parameterizations of the deuteron form factor, which are, of course, far fewer than for the proton, but nonetheless, we use all that are available. And we find that the fixed rational 1-3 function was the most robust fitter. And the robustness is quantified in terms of this root mean square error, just as it was done for PRAD, which includes the difference between the input and extracted radius and the statistical variation. We decided on the amount of beam time based on constraints coming from the coordinate detector DAC, maximum DAC rate, which is 25 kilohertz, and the maximum power allowed on the Hall-B Faraday cup, which is 160 watts, which allows us, with the target density of 2 × 10⁸ deuterons per centimeter square, we can have 30 nanoamps at 1.1 GeV and 70 nanoamps at 2.2 GeV, which gives us a total requirement of 40 days, which include time for the 2 different beam energies and empty target runs lumped together, and additional time for recoil detector calibration, commissioning, and the calorimeter checkout. The systematic uncertainties were extracted in the same way as done for the PRAD, namely by using 10,000 mock data sets, mirroring them with systematics and statistics, and then looking at the difference between those, the smeared and the unsmeared, to get to the relative uncertainty. And we find that the largest contribution comes from the event selection and the efficiency of the recoil detector. And with these, we have shown that we estimate the uncertainty to be about 0.22%, which is about half of what is the best measurement or best result, current result, which is a reanalysis of old data by Sick and Troutman. And so our expected result is about a factor of 2 smaller uncertainty, which gives us sensitivity to this difference between the muonic and the regular deuterium spectroscopy results. This was not the first time we proposed this experiment. We had proposed it earlier in PAC 45. However, it was deferred, asking us to complete our PRAD analysis and to have a concrete plan for calibration of the detector. And now we have both. We have finished PRAD and we have a concrete plan which we are continuing with for measuring the efficiency of the detector. I will skip these since we are running out of time, of the TAC questions, which we have already answered and sent the responses, but they're here, and I'll summarize. So we propose a new high precision measurement of the deuteron charge radius using electron-deuteron scattering. This will use the spectrometer-free method, calorimetric method of the PRAD experiment, pioneered by the PRAD experiment. And we will use the PRAD2 setup with an additional cylindrical silicon strip-based recoil detector. This will allow us to reach the lowest Q-square probed in electron-deuteron scattering, while at the same time cover a large Q-square range spanning about 2 orders of magnitude, and that these together allow us to reach a precision of about 0.2%. And we request 40 PAC days at 1.1 and 2.2 GeV beam energy. Thank you.
Thank you very much. I call on the first reader of the proposal for questions. Stefan, please.
Yeah, thank you very much for the presentation. I have a couple of questions. The first one, which comes out of the theory report and was mentioned already today in our internal discussion, was the quality of the radius correction calculation in deuterons. And it was mentioned by the theory group that this is far more, even more challenging than for the protons. Can you just comment on that?
Yes, the calculations for the deuteron will also be performed by the same group of theorists who are working on the PRAD problem. And in fact, there is considerable work being done for both PRAD and DRAD, and the work that is being done for PRAD will carry over to the deuteron as well. So currently, the group that is working on the PRAD radiative corrections will are also working on the DRAD at the same time.
Okay. Another question which just came to our mind. You know, you have these quasi-elastic proton reaction as a background. Can you actually turn the problem into a virtue and make use of the interactions with the proton? So you have a recoil proton that you extract information from that as a cross-check for the deuteron?
You mean extract the proton radius from the...
Are the uncertainties for the deuteron wave functions and everything else too large to get any information out?
Basically, the experiment is designed to reject those protons. So in principle, we could accumulate those protons and look at them as well. I'm sure if we can think of physics problems to solve with those protons, it can be used, yes. But for us, it is a background which we are trying to reject using this time difference and azimuthal angle difference.
Yeah, this I understand. It just came to my mind. Sorry.
Yeah.
And there was another issue raised by theory. This was the quality of the simulations on the breakup. And now you have done, in principle, you have shown that you pretty safely can reject background from breakup.
Yeah.
So uncertainties in modeling might not be very strong. But can you remind me again, what is the error budget on rejecting this background on the quasi-elastic or on the breakup reaction? So if you have a larger uncertainty on this, will it spoil your radius measurement?
So that what that affects basically is this efficiency of the recoil detector. That's all those uncertainties are lumped into that category, where how well are we separating the proton and the efficiency of the detector itself. And so that is one of the larger uncertainties. However, the point that was raised by the theory colleagues is more that would affect the even lower angles. This really doesn't affect the angles we are interested in. It would be at the threshold of the reaction.
Okay, thank you.
If Stefan doesn't have any further question, maybe we can now jump to Concertina. Concertina, any questions?
Yeah, very nice talk. Thank you very much. I have just a very quick question since you are on this slide, because to my question about the differences in the error table for PRAD and DRAD, you just answered that in the case of DRAD, you have taken the best estimate for both the HCAL and the GEM. So do I understand correctly that actually even in the case of DRAD, if the overall upgrade for whatever reason is not successful, that will not be the limiting factor, because the limiting factor in the error budget comes from the event selection and from the radiative correction. Is that a fair assessment?
That is correct. Yeah,
okay.
That is correct. So those are the two major event selection and inelastic efficiency.
Yeah, thank you. That was it.
Very good.
May I since I cannot raise my hand.
Yes, please, Charlotte. Please ask your question.
Yeah, I mean, just a quick question. Is it a secret who the theorists are who are working on that, and what is the timeline? Because I'm fully aware that these are non-trivial calculations, neither for the proton and for the deuteron it's even harder.
Akushevich from Duke University and his collaborators, those are the main people from Duke who have been working, and Haiyan mentioned another theorist from Mainz who has already completed some of the work.
Okay.
Yeah, it's not a secret.
From Mainz, that was Hubert Spiesberger, is that correct?
So maybe Haiyan can remind us again what was the person from Mainz. I don't remember the name right now.
Hubert Spiesberger. Yeah.
Oh, Spiesberger.
Thank you. Is there any other question from members of the PAC?
Yeah, I like to ask the same question that Charlotte asked. What is the time scale that is you anticipate for having these radiative corrections for the deuteron, say, which I think is sort of uncharted territory to me?
Yes, for that I would request Haiyan to answer that question, because it's her. She's leading the group that does this calculation.
Well, I'm actually motivating our colleagues to do the calculation. And in fact, if I'm not mistaken, we in principle should already mention or give a reference in the DRAD proposal that Igor Akushevich and collaborators have a paper on ED radiative correction already. And so in terms of timeline, I would think that it will be after the PRAD2 radiative correction calculation. So we will be looking at this 3 years, 3+ years. But the earliest will be after 3 years for radiative correction for the DRAD.
Thank you very much.
Sorry, make sure I understand. So 3 years for PRAD?
No, I'm sorry. For DRAD, I think the earliest will be after 3 years, counting, from the proposal is approved. And for PRAD, we hope that in the next 3 years. So DRAD will be after that.
Okay, thanks for the clarification. P and D sound very similar.
Okay, I think that is a good point to stop. And let's switch speakers again. The last presentation of today is by Eric Fuchet of a proposal for 2 photon exchange measurement. Please, Eric.
Can you hear me?
Thank you.
Okay. So I'm Eric Fuchet hello everybody. I'm Eric Fuchet from University of Connecticut, And on behalf of my fellow co-spokesperson, Sharon Al-Salmi and Bogdan Moshchekovsky, I want to present you the experiment to measure the two-photon exchange contribution on the elastic electron-neutron scattering. The main motivation for this experiment is to better understand the nucleon form factors, which are critical to understand the nucleon structure. Form factors are measured by elastic electron-nucleon scattering. In the one-photon exchange approximation, illustrated by this diagram, the cross-section of this process can be written as the product of the mod cross-section times the linear combination of the squared Sachs form factors, Gm magnetic and G electric. The Rosenbluth technique can be used to separate Gm squared and G squared based on the dependence of the reduced cross-section sigma r defined here in epsilon, which is the virtual photon polarization. The basic idea is to perform two or more measurements at same q square and different epsilon. On this graph here, illustrate two fictive reduced cross-section measurements at two values of epsilon and fitted by a linear function. So the slope of this function is the electric part of the cross-section, and the intercept at zero, the magnetic part. This technique has been used extensively to measure the Rosenbluth slope for the proton and extract GEP. Here are presented slack data of reduced cross-section on the proton as a function of epsilon and for different q squared values up to 3 GeV squared. And you can notice that the linearity in epsilon has been well tested up to 3 GeV squared. In elastic electron-neutron scattering, the last measurements attempting to use this Rosenbluth technique were from Daisy in 1972, and their results showing Gn squared as a function of q squared with the error bars shows that their experimental accuracy was not sufficient to extract any meaningful result from this technique. On the proton, global fits of the Rosenbluth slope have been performed on the existing data. This graph from a PRL in preparation shows the most recent of those global Rosenbluth fit, so the black solid curve. And this fit includes JLab data, the last JLab data at 12 GeV. And it is compared to the global fit of the polarization transfer data, which is the blue dashed line, the curve. At q square equal 4.5 GeV square, where we want to do a measurement, the Rosenbluth slope is 0.087 plus minus 0.01. And what we can see is on the full q square range display on this figure, the results obtained with the Rosenbluth method and the polarization transfer method show a large discrepancy. So there's a missing contribution between the two, which is likely to be the two-photon exchange. So until GEP1 at Jefferson Lab in 2000, the one-photon exchange approximation was accepted to be sufficient. So the discrepancy that we just reviewed between Rosenbluth and polarization transfer made the two-photon exchange, the investigation of the two-photon exchange mandatory. Many experiments were dedicated to measure this two-photon exchange, including dedicated Rosenbluth and positron-proton, electron-proton scattering. This graph shows JLab reduced data on the proton as a function of epsilon and different values of q squared compared with fit from polarization transfer data, the dotted lines, and those same fits corrected with two-photon exchange contributions. That's the solid curves. And those data, the data agree pretty well with the correction, with the predictions, including the two-photon exchange correction. However, those data are also linear, show also some linearity from mid to high epsilon. And so this linearity does not exclude two-photon exchange. And So that was on the proton, and on the measurement on the neutron will bring new insight to this physics. The two-photon exchange contribution was never measured for the neutron. Blondin, Melnichuk, and Chong gave a prediction on the impact of the two-photon exchange contribution to G over Gn. So on one of their predictions here, showing mu G over Gn as a function of Q squared, so the blue is uncorrected mu G over GMN parameterization, which is fairly old, by the way. And the red shows the mu G over Gn measurement, predicted measurement that one would have measuring the slope between epsilon, Rosenbluth slope between epsilon 0.2 and epsilon 0.9. And the green shows the mu Gn over Gmn value predicted from a measurement of the Rosenbluth slope between epsilon 0.5 and epsilon 0.8. And we may notice that even on a relatively modest epsilon range, we may have a measurable effect. The main goal of the experiment we propose is to perform a Rosenbluth measurement on the elastic electron-neutron scattering for the first time since 1972, with 10 times improved accuracy. With such a measurement, we're hopeful to extract the two-photon exchange contribution on elastic electron-neutron scattering. This experiment will use the equipment and some of the data from the already approved GMN experiment in Hall A. This table showing the kinematic settings for our two measurements. So shows the blue is our low epsilon, which is already approved, and the red is for the high epsilon settings, which we request for this measurement. Here's a view of our experimental setup for the low epsilon. The 30 micrograms electron beam arrives here on the 15 centimeters liquid deuterium target. The scattered electrons are measured in big byte, the big byte spectrometer, and the recalled protons and neutrons are measured on the super big byte spectrometer. Let me present you a few key experimental parameters and analysis features for this measurement. The electron-nucleon luminosity is 2.8 times 10 to the 38 per centimeter square per second. The big byte spectrometer has 32 millisteradian solid angle with 1% momentum resolution and better than 2 millirad angular resolution. With such characteristics, W square, which is the missing mass of the electron-nucleon system, can be reconstructed for the elastic peak with a resolution of 0.25 GD squared. So here is represented our Monte Carlo generated quasi-elastic electron-nucleon sample in W squared. And this is compared to the W squared distribution of our inelastic resonant electron-nucleon sample on the right. And you can see, comparing those two graphs, that it's fairly easy to set a cut, a selection cut in W squared to exclude a large part of this inelastic background. The calorimeter threshold is 3 GeV squared to select a 4.2 GeV average elastic peak, and the projected single rates with such a threshold for big byte is 8 kilohertz. Super big byte spectrometer has a 71 millisteradian solid angle with 5 milliradian angular resolution. a time resolution of half a nanosecond over 25 nanosecond time of flight, and energy resolution, which fortunately we do not rely on for the analysis, of 40%. So the identification between quasi-elastic proton and quasi-elastic neutron is made with the information from the hadron calorimeter HCal. So here is represented the difference between the reconstructed position of the nucleon in HCal versus its projected position. And the projected position is made assuming that those are all neutrons. So here this is, in this direction is X, the non-dispersive direction, and in this direction, it's the horizontal is the axis is the dispersive direction. And so this structure here centered on y equals 0 is the neutrons which are indeed not affected by the magnetic field, the SPS magnetic field, whereas the protons, which are bended upwards, are shifted by about 1 meters. And so that's how we identify between protons and neutrons. The calorimeter threshold is 0.10 GeV for 90% efficiency of the quasi-elastic nucleon, which deposit about 0.20 GeV in the HCal scintillator materials. And with such a threshold, the projected single rates are about 3.3 megahertz. So combining the big byte and HCal rates on a 30 nanosecond coincidence window, our trigger rates are about 800 hertz, including about 180 hertz of quasi-elastic, including 1/4 neutrons and 3/4 protons. This experiment will use the technique proposed by Durand in 1959 to measure. So the idea is to measure simultaneously quasi-elastic electron neutron and electron proton of deuterium in order to measure the ratio of the neutron cross-section sigma n over the proton cross-section sigma p. So the main advantage of this technique is many effects such as the nucleon Fermi momentum, the nuclear binding effect, cancel entirely in the ratio. Other effects such as the nucleon charge exchange in final state interaction, the inelastic electron-nucleon contamination cancel partially. So they will still contribute to the systematic uncertainty of the cross-section ratio, but not as much so as they would contribute to the errors on the individual cross-section. And this technique has been used extensively to measure GMN, including recently at JLab and MINDS. This technique has also been discussed to use for GMN at JLab back in 2002. So the main idea is to measure Rn/P, which is the ratio of the quasi-elastic electron-neutron yields over the quasi-elastic electron-proton yields. Multiplying Rn/P with F-core, which encapsulate radiative corrections, hadron efficiencies, and acceptances, etc., we obtain R-corrected. R-corrected can also be written as the ratio of the neutron over the proton cross-section. Now, measuring R-corrected on 2 epsilon point and taking the ratio of the two, we obtain A, which is our experimental observable, and which can be written as the product of B, which depends on the proton Rosenbluth slope SP, and this term here, which depends on the neutron Rosenbluth slope Sn. So in other words, measuring A and knowing SP, which we do, we can deduce the neutron Rosenbluth slope at Sn. As discussed earlier, with the technique we use, the dominant source of systematics are cancelled out. Say again?
5 minutes left.
Oh, okay. Okay. So the top table shows the the top table shows the remaining systematic uncertainties for the individual kinematic measurements, which add up to about 1%. And the remaining source of systematic uncertainties to the neutron two-photon exchange contributions come from SP, which contributes directly to SN, and from the knowledge, the uncertainty on the knowledge of mu G over Gn, which will combine to the SN uncertainty to the two-photon the total uncertainty on the two-photon exchange contribution term. We've requested 48 hours total, including 24 hours beam on target for production, 8 hours beam on target for systematic checks, and 16 hours for setting change, including a big byte move and a beam pass change. So under this assumption and assuming the same proportion of two-photon exchange contribution to assuming the same proportion of two-photon exchange contribution and G over Gm contribution to the neutron Rosenbluth slope, as in the paper from London, Melnichuk and Chang, but using the Gn over Gmn review value from the form factor review by Perdizat et al. In 2015, we expect the NTP contribution to be 0.063 plus minus 0.010 plus minus 0.012. And this graph shows the contribution to the Rosenbluth slope due uniquely to G over Gn, which is the blue dashed, with uncertainty, the blue dotted area. The total projected slope, neutron slope, including two-photon exchange, is represented by the solid magenta curve. The red, the black solid line with the red area represents the uncertainty that our measurement will set to the slope, and the dotted area shows the magenta. The magenta dotted area shows the total projected photon exchange uncertainty. This is the GMN schedule. So the black and blue lines correspond to the already approved schedule, and the red lines correspond to the addition to the schedule that we request for this experiment. And this can be inserted fairly easily into the currently approved schedule. So to conclude, I want to recall that the knowledge on the two-photon exchange contribution is essential to shape our understanding of the elastic electron nucleon scattering and hadron structure. The experiment we propose will provide the first Rosenbluth measurement of elastic electron neutron scattering since 1972, with 10 times improved accuracy and at a higher Q square of 4.5 GeV squared. The result will help advancing the theoretical understanding of the two-photon exchange, and this experiment can be inserted smoothly in the currently approved schedule with 2 PAC days requested. Thank you.
Thank you very much also for being on time. So we now have first questions from the first read of the proposal, who is Steve Dittman. Please, Steve.
Steve Deitman, please. Thank you very much. We've had good conversations over email, and this helps. However, I'm still confused just a little bit about various things. What is your actual measurement? It's sigma L over sigma T, but are there any form factor measurements associated with this measurement?
So the GN over GMN for the purpose of this measurement, the GN over GMN is it's not assumed. We rely on existing knowledge. okay, let me rephrase that. What we will measure is the neutron Rosenbluth slope, and the two-photon exchange. The two-photon exchange can be calculated from existing knowledge on G over GM. But our core measurement is actually the neutron Rosenbluth slope.
Yeah, I understood that. Would it help at all if you were to try to measure GEN to make sure you're consistent in some level?
Well, that would help. But if I can, there is another. So why did we settle on this Q-square value of 4.5 GeV squared? Is that because there's this GENRP measurement at the same Q-square kinematics? So yes, that will help a lot. But that's already another measurement in itself. We don't.
Yeah, I understand. Yeah, that will get GMN. But do you see value in trying to measure GEN from the same data? That's my question.
Well, I mean, GN over GMN. I mean, okay. So by the way, Bogdan, please, and enter the conversation as you like. But what I mean, as far as I know, whatever value of G, well, it's not as far as I know. Let me be a little bit more affirmative here. What this measurement, the measurement that we have, will measure is the slope. And if you want to get GN over GMN from the slope, you will have to have some assumption about the two-photon exchange. So that's looping around, so to speak.
Yeah. Okay, thanks. Could we go back to slide 5?
Slide 5.
I believe it's 5. That's for a proton. There we go. Yeah, so this is proton, and there is no data at 4.5 for the proton?
For the proton, I mean,
it was in that paper.
Data in that range, but I don't think. I mean, from this graph, there doesn't seem indeed to be any specific data point at 4.5 GeV squared exactly, but.
Yeah, I saw it because it was in your paper
that
you sent me, but it's not in the figure. Okay, so, but what you're going to do is, how will you get the 1 PE? You said good that it was from previous data. Is there any data you can use for the 1 PE, or how will you understand what that is?
Okay, so the current assumption we had on G over Gn so it comes from this form factor review, which has a parameterization for mu G over Gn with so it's a fit from the G over Gn data obtained with recoil. With polarization transfer, and we have again this GNRP measurement already approved, which will also measure GN over GMN with polarization transfer, and that will be what our one photon exchange reference will be.
Okay, thanks. Last question is neutron efficiency uncertainty is not in your table of uncertainties. Are you going to measure it extremely accurately?
Neutron efficiency. I mean the neutron efficiency. So these would be the neutron efficiency. Good call. It should be in the. So I mean that sort of measurement will be. I mean. It will have to be also not specific to our measurement. It will also have also to be made by GMN. And yeah, by the way, this nucleon misidentification. So it includes that. It includes the neutrons which by accident that we know by accident ended up here, and the protons that we know by accident ended up here. Accident by like rescattering or whatnot. So that's part of the that's part of the efficiency of the efficiency of the nucleon detection.
Okay, that's enough for now.
But we expect the proton and the neutron efficiency to be the same. The detection of the proton and neutron efficiency should be the same. Well, the acceptance may be different, but we have the Monte Carlo to evaluate the acceptance.
And I just want to mention, Eric, that Michael and Andrew have both chimed in on the chat to suggest that same thing, that the proton and neutron efficiencies are very high and very similar.
Yeah. Thank you. I was not looking at the chat. I'm still in full screen mode. Thank you.
Right. I know you can't see it, but the others could check it there also, and the cancellation in the ratio, since you're as long as they're similar, then it's canceling in that ratio.
Yeah.
Very good. So Steve, you can maybe take a quick look at the chat.
Yeah, I am. I'm done. Other people can.
Dufang, do you have any questions?
Yeah, so it's more about the theoretical interpretations. So could you go back to the slide 15? It's the same slide as Steve had a question. 16, sorry. Yes. Yeah. So the difference between the dashed line and the solid line, so is that what's supposed to be the two photon exchange effects?
That's how we evaluated it. So the idea is, so what we did was, so in this paper from London, the ratio between the two photon exchange and the GN contribution to the slope was identical. So in other words, I think the two photon exchange to GN in their paper was basically doubling the slope. So we made this assumption. Of course, we don't know yet what it is, but that's the assumption we made, that basically the two photon exchange was doubling the slope. We don't know yet if it's true, of course, but that's why we want to do our measurement.
Okay, and so the dashed line is for the polarization transfer data. So that one, I assume there's no photon exchange effect at all.
So yeah, that's the blue dashed is just the GN over GMN that we would that we expect to obtain from polarization transfer data. But again, it would actually still need to be measured too.
Okay. And so my second question is about the theoretical interpretation. So say, for example, in your experiment, you measured the two-photon exchange effect, but you would in principle want to compare with any theoretical calculations, right? So what's the current status for on the theoretical side? I mean, on the two-photon exchange?
Well, I mean, we used we used this paper as a reference. I mean, I don't think there are any. So I mean, I can bring it back to here where you know there are calculations for the two-photon exchange.
But for this plot, there's no error bar, nothing. It's just.
Yeah, I agree. I agree.
Okay.
But I mean that is we are.
Okay, I see. So as far as I can tell from this plot, currently the status on the theory side of the two-photon exchange is kind of behind what your experimental measurement would be. Okay.
Yeah.
Okay, that's not your fault. Thank you.
Yeah. Okay. Thank you.
Okay, I'm done with my question.
All right. So is there any very urgent question from any other member of the PAC? That is not the case. Then let's thank Eric again. Thank all the presenters and their colleagues from this session. The PAC has now to switch over again to the Zoom meeting. To everyone else, I'm saying goodbye and hear you or most of you again tomorrow. Thank you.
Okay.
What is Zoom? Which Zoom is it?
Blue Jeans. Sorry,
no, Blue Jeans. Regular Blue.
Much better.
When,
Thanks.
When we were in this morning, the same ones this morning. Yeah.